continue with the problems on an unequal angle 1.5 meter long of truss is connected to a gusset plate. It carries an ultimate tension of 230 kilonewton. Design the section using bolted connections. Assume Fy equal to 250 MPa and Fe equal to 410 MPa. So here the sizing of the angle section is not given, so we have to do the preliminary sizing. So given data, design load is 230 kilonewton, type of connection is bolted connection. So whenever you have a bolted connection and size of the angles is not given, you increase the area by 15 percentage. Now by using clause 6.3.1, we have TDG equal to AG into Fy divided by gamma m naught. So here AG required, you just keep AG required here, take gamma m naught to the numerator of the left hand side and Fy to the denominator, and increase the value by 15%. Increasing 15 percentage in the sense multiplying with 1.15. So we get an area of 1163.8 millimeter square. So from steel table, let us try with an unequal angle section by keeping the gross area in mind. So let us keep the required area as 1164 millimeter square approximately. So let us select ISA 80 by 50 by 10 mm. Therefore, AG provided equal to 1202 millimeter square. Now, AG provided we have calculated from the steel table, or you can also calculate it. The longer leg connected to the gusset plate. Let us assume the longer leg is connected to the gusset plate. That means 80 mm the side or leg is connected to the gusset plate, and 50 mm leg is the outstanding leg here. The diameter of the bolted connection also we need to design here. The diameter of the bolt is calculated by N1 formula is D equal to 6 into root T. So 6 into 10 root of 10, it is 18.97. Let us assume the diameter of the bolt equal to 20 mm. So number of bolts required equal to design load divided by bolt value. Therefore, the bolt value is the minimum of the design strength due to shear and design strength due to bearing capacity of the bolt. So design capacity of the bolt VDSB equal to VNSB by gamma MB. So here let us assume this ns equal to 0. If ns is equal to 0, ASB will tend to 0. We consider only NN and A and B. You calculate A and B. A and B is 0.78 times pi by 4 into 20 square. It is 245.044 millimeter square. Now Fu is equal to 400 Newton per millimeter square here, because the grade of the bolt we have taken 4.6. Here only we are assuming the thread is intersecting the shear plane completely. No shank is involved. Therefore Ns is equal to 0. So VDSB works out to be 45.27 kilonewton. Now bearing the capacity of the bolt in bearing, VDPB equal to 2.5 kb dt Fu divided by gamma MB. For simplicity, let us take kb equal to 0.5. Therefore, VDPB works out to be 82 kilonewton. Out of these two values, least value is the bolt value. So 45.27 kilonewton is the bolt value. Therefore, number of bolts required equal to design load 230 divided by 45.27, approximately 6 numbers. Therefore, now let us check the capacity of the connection with the 6 number of bolts provided. So gross strength of the section works out to be 273.18 kilonewton, which is greater than 230 kilonewton. So it is safe in yielding. Now the net section rupture, it is a preliminary sizing because the angle section is not given. We have chosen the section. Therefore TDN equal to alpha into AN into FU by gamma M1. Here number of bolt is equal to 6 we have taken. Therefore alpha for more than 4 number of bolts, alpha is equal to 0.8. Therefore this is there in clause 6.33 page number 33. Therefore an can be calculated as the net sectional area. So the net sectional area for connecting leg is 80 minus 10 by 2 minus diameter of the hole into thickness, and for outstanding leg there is nothing to deduct like diameter of the hole, only the half of the thickness is to be deducted. So 50 minus 10 by 2 into 10, 450 millimeter square. So the total area is 980 millimeter square. So TDN works out to be 257.15 kilonewton, again greater than 230 kilonewton. So it is safe in net section rupture. Now coming to the block shear you calculate what is ln is 30 mm here. Okay, then this edge is, or this particular leg is 50. The total length of the connected leg is 80 mm. right? So the edge distance, let us calculate, it is 35 mm, 1.5 times the diameter of the hole, and pitch distance is 2.5 times the diameter of the bolt, so it is 50 mm. Now LV, LC, LT and LN. So LV is 35 plus 5 into 50. We have clearly discussed that in the previous videos. Then LC is LV minus total how many number of bolts are there, minus 0.5 into diameter of the hole, it is 164 mm. Then LT is equal to 30 mm, Ln equal to 19 mm. Now from class 6.4.1, page number 33 and 34, we have TDB1 and TDB2. For that, we have to calculate AVG, AVN, ATG, and ATN. So AVG equal to LV into T, AVN equal to LC into T, then ATG is LT into T, and ATN is equal to Ln into T. So we get 2850, 1640, and 300 millimeter square and 190 mm square. Therefore, out of upon substitution, we get TDB1 equal to 430.035 kilonewton and TDB2 equal to 347.693 kilonewton. Therefore, out of these two, the least value is equal to 347.693 kilonewton, which is again greater than the applied tension 230 kilonewton. Hence, it is safe. So in this problem, the length of the member is given as 1500 millimeter or 1.5 meter. So we need to check the slenderness ratio. So slenderness ratio equal to effective length divided by R minimum. So R minimum is nothing but minimum radius of gyration. So it is a steel section. So from the uh, steel table, R minimum can be calculated, or R minimum value we get. R minimum value from the steel table we get it as 10.6 mm. So slenderness ratio lambda equal to 1500 divided by 10.6, it is 141.501. So from table 3, page number 20, uh, so we get lambda equal to 350 for tie in a truss, and also another value, the with the reversal of stress, we get the slenderness ratio equal to 180. So when you compare these two values with 141, 141.50, the slenderness ratio is less than these two maximum values. So this is how we can solve a few problems when the size of the angle is not given and also the bolted design is not done. We have to do all this, and also if the length is more the of the section, then we have to do the check for slenderness ratio also. The table number 3, page number 20 gives a clear idea about use of slenderness ratio and check for slenderness ratio. So in the coming video lecture, let us go for the concept of lug angle and also the design of lug angle. Thanks for watching.